Now we turn to vectors over GF2. Here's an example of addition of GF2 vectors. We're adding them entry-wise, and of course, 1 plus 1 is 0, 1 plus 0 is 1, and so on. Now, we'll use the notation sometimes 1, 1, 0, 1 instead of the list 1, 1, 0, 1. So here's another example. What's 1, 1, 0, 1 plus 0, 1, 1, 1? And the answer you should get is 1, 0, 1, 0. Now let's see how we can use GF2 addition to achieve perfect secrecy in a cryptographic sense. So we're going to represent encryption by n-vector addition over GF2. So let's imagine that Alice and Bob agree on this key. It's a 10-vector over GF2. And later, Alice wants to send a message to Bob. Here's the plain text. She encrypts it by adding P and K, the plain text to the key, to get the ciphertext. So here's the ciphertext. When Bob receives C, he can decrypt it by subtracting, which is the same as adding, the key. And he gets back the original message. Now, I claim that if the key is chosen according to the uniform distribution, this scheme is perfectly secret. For each plain text, there's a function that maps the key to the ciphertext. Namely, given the key k, it maps k to k plus p. Now, this function is invertible. What that means is that if the key k is chosen according to the uniform distribution, the output will also be distributed according to the uniform distribution. Now, that doesn't depend on which plain text we chose. Regardless of the plain text Alice chooses, the distribution of the output is the uniform distribution. So an eavesdropper learns nothing about the plain text by looking at the output. Here's another use of the same idea. Suppose I have a secret, the midterm. So I'll represent it as an n-vector over GF2. Now, I want to provide it to my teaching assistants so that I can go on vacation. However, I don't completely trust my TAs. One of them might be bribed to give away the midterm before it's time. So the solution is to provide pieces to the two teaching assistants. I want the two of them jointly to be able to reconstruct the midterm, but I don't want any one of them acting alone to know anything about the midterm. So here's the solution. I start by choosing a random n-vector over GF2. Let's call it VA. I then compute VB by subtracting, which is the same as adding in GF2, subtracting VA from V. Now I provide VA to Alice, one of my TAs, and VB to Bob, the other TA. And I leave on vacation. What does Alice learn from her part? Well, all she receives is a random n-vector. Well, what about Bob? The part he receives is the output of a function f of x equals v minus x, where the input is chosen according to the uniform distribution. Since this function is invertible, the output is also distributed according to the uniform distribution. So he learns nothing. Now, seems like a really simple trick, but RSA just introduced a product based exactly on this idea. Their product splits a password using essentially the technique we just showed so that it can be stored on two separate servers, making it more secure. Here's another application of GF2. This is the lights out puzzle. It's a grid 5 by 5 consisting of buttons that light up. When you push a button, it toggles the light. So if the light is on, it turns it off. If the light's off, it turns it on. It toggles the light on the button you push, but it also toggles the lights on the buttons immediately above and immediately to the left and right of the button you push. So if I push this button, Well, and the goal is to push enough buttons to turn off all the lights. All right, I'm obviously not very good at this, but I know linear algebra. So I'm going to look at how we can use linear algebra to figure out how to solve lights out. So given a configuration of lights, we want to figure out what sequence of button pushes will turn off all the lights. We're going to represent the state of lights out using a vector. There's going to be an entry in the vector for each light in lights out. So for 5 by 5 lights out, that means there are 25 entries. And these are vectors over GF2. Here's a representation of the state of lights out. I'm using these black dots to represent lights that are on. Now, the trick is we can also represent each button as a vector over GF2. We represent a button by the GF2 vector with 1s in exactly the positions that are toggled when we push that button. Remember that in GF2, adding 1 means flipping a bit. If you add 1 to a 1, it turns it into a 0. If you add 1 to a 0, it turns it into a 1. Let's look at the 3 by 3 case. So suppose this is the state of lights out, and we push the button in the top left. Well, the button in the top left toggles the light in the top left, the light immediately to its right, and the light immediately below it. So this is the move vector corresponding to that button, where the dots represent 1s. If we add this vector to the vector representing the state, we get this vector, which represents the state obtained by pushing that button. Similarly, given this state, we push the button in the middle, it toggles the light in the middle, the lights directly above and below, and the lights to the left and right, resulting in this state. Finally, from this state, if we push the button in the bottom right, it toggles these positions, giving you the state in which all the lights are out. The key idea here is when we use vectors over GF2, adding a vector toggles exactly the positions where the vector we're adding has 1s. So we can use GF2 vectors to model the process of pushing buttons in lights out. The question is, which sequence of buttons will lead to the configuration in which all the lights are out? Here's some simple observations. By the commutative property, the order in which you push those buttons doesn't matter. Also, if you add a button vector twice, they cancel out. So really, instead of trying to think about the sequence of buttons we push, all we have to do is figure out which set of the button vectors we have to push. That is, which set of the button vectors will sum up to the vector representing the initial configuration. Thus, we've reduced the problem of solving an instance of lights out to which set of button vectors sum up to the vector representing the initial configuration. A more general version of that problem is, given a bunch of vectors over GF2, find a subset whose sum equals some target vector S.